Good morning. Yesterday or Friday, we went over how or an ice table, how to use it, what equilibrium is, or extended our understanding of equilibrium. Today, we're going to look at how to use an ice table to determine the concentrations given proper information. So, if we're given the initial concentration, and as we are in this question down here, which is kind of hidden, the Kc value at a certain temperature. So we said, right, our RICE tables, I'll still call them ice tables. RICE tables stands for reactions, initial concentration, change in concentration, and equilibrium concentration. So here we're basically going to use the ice table to keep track of stuff and then perform a calculation with what we have. So first step in this is, or a step, I'd like to do it first, is to determine the equilibrium constant expression for the equation. Well, here we have everything at 1 to 1. So we have the Kc is equal to the products, which would be helpful if I had something in front of me. Which is H2 gas, CO2 gas, both raised to the power of 1 over H2O gas, and carbon monoxide gas. So there's your equilibrium constant expression. Now, next step, we're going to need the concentration of the initial reactants. So we have a 500 milliliter container. Okay. We initially put 2 moles of each reactant is placed into the container. So for both of these cases, the concentration is equal to 2.0 moles. Concentration is equal to N over V. And our liter container, or half a liter container, we have a 4 mole per liter concentration of our initial reactants. So once we're here, now we can go start to plug into our RICE table. Now again, I don't have the equation written here, but it's going to be H2O gas plus CO gas yields CO2 and H2O. Now again, in this situation, it's a 1 to 1 to 1 to 1 ratio. That is useful for us. So we have initial. We have 4 moles per liter here. We have 4 moles per liter here. We're going to make an assumption that the container was empty when we entered those in. So there is initially no carbon dioxide or hydrogen gas in those. Now we don't know what the change is. We have to make an assumption. We're going to say that we use up X amount of the water. Okay. Don't know what X is. We're going to find X or find values of X. Now, because it's a 1 to 1 ratio, we're going to have X. We're going to use up X amount of the carbon monoxide. It's also a 1 to 1 ratio. So we're going to add X amount of the carbon dioxide. And for similar reasoning, we're going to add X amount of the hydrogen gas. So now we can determine an expression for each of our final concentrations. Just 4 minus the change of X. Now, we can take these and plug them into our Kc expression. Well, we know or the question tells us that we have 4.2 is our Kc. We have X for our hydrogen gas. We have X for our carbon monoxide. We have 4 minus X for our concentration of our water. We have 4 moles minus X, or 4 moles per liter minus our concentration for our carbon monoxide. This can be simplified. Now, in this situation, what we're able to do is to take the square root of this side of the right-hand side, because both the numerator and the denominator are squared. This is not a normal process. I'm going to show you a approximation method in a minute. And since I take that, I'm going to take the square root of that. Square root of 4.2 is 2.05 approximately. That's equal to X over 4 minus X. Now, this is just a simple rational equation. First, yes. So we have 8.20 approximately, or then minus 2.05x is equal to x. 8.2 is equal to 3.05x, adding our 2.05. 8.2 divided by our 3.05 is x is equal to 2.69. Okay, now that's x. So going back to our ice table, we need to figure out what we have. Well, we have the concentration of the hydrogen at 2.69 moles per liter. Same thing here. And then over here, we take away 2.69 from 4, and we end up with 1.31 moles per liter and 1.31 moles per liter. So the calculations we did down below allow us to solve for our unknown x, and then we have to interpret what that means within the expression, or within the equator, the reaction. So if we were to plug these numbers in, we get our 4.2. Now this worked for this situation because I've done all that, sorry. And I've done that too, so we'll skip those when they did it on one page. As I said, this one works because we have both the numerator and the denominator squared in that equation. We can't really use this in, or this situation in most of what we're going to run into. We can solve quadratic equations using the quadratic formula, which I know everybody loves so much. But for our purposes in high school, we're going to use an approximation method. Almost all, but what we're going to do is using the approximation method. Now, this approximation method works when very little of the reactants become products. Okay. So, general rule of thumb, if it is less than 1.0 times 10 to the negative 4. So if your Kc is this small, we get to use the approximation method. If we go much bigger than that, the approximation method starts to deliver worse and worse answers for this. Okay, so we got the reaction of nitrogen and oxygen to form nitrogen monoxide gas. The Kc of this expression is 4.2 times 10 to the negative 8. That's definitely small enough for us to use our approximation method. So here's some more information. We put 0.085 moles of nitrogen and 0.038 moles of oxygen into a rigid container. We want to know the concentration of the nitrogen monoxide at equilibrium. Well, here's our equation. 1 nitrogen plus 1 oxygen gives us 2 nitrogen monoxides. And I'm just going to go back and find my values. Nitrogen. So because it was a 1 liter container, we take our concentration, divide by 1 liter, we get our 0.085 moles per liter, 0.038. And we have to make the assumption that there was no nitrogen monoxide in that container to start with. Now, I say this guy is X. This is a 1-to-1 ratio. So this reactant uses up X. This is a 2-to-1 ratio. Therefore, we're going to add 2X to that. Again, going back to the ratio that we have in the chemical reaction. So we have 0.085 minus X, 0.038 minus X, and we have 2X as our final. Now I have not yet created my equilibrium constant expression. So Kc is equal to the nitrogen monoxide gas concentration squared from our reaction over our nitrogen gas raised to the power of 1 times our oxygen gas raised to the power of 1. So going to this, our Kc is small, very, very small. And actually I have to go back and figure out what it is. 4.2 times 10 to the negative 8. We have 2X, which is our concentration of our nitrogen monoxide squared. We have 0.085 minus X times 0.038 minus X. Now, here is where the approximation comes in. Because this Kc is so small, that means this X is going to be small. So this X, in comparison to the 0.085 that they started with, is very, very small. Same with the 0.038. Compared to the 0 of the nitrogen monoxide we started with, it is infinitely larger. So because we're strongly favoring the reactants, we can take this expression and simplify it. We're just going to say that the X is so small in comparison to the initial concentrations that we can effectively ignore it, and we're going to get an answer that is approximately correct. These X's are small in comparison to that, but it is very, very large, infinitely larger than comparison to the 0 that we started with here. So we have to keep this X in, but these X's can be ignored for the sake of brevity. So a little bit of math work. Make sure that we square the 2 in that. And now again, we have a rational equation that we can solve. Multiply both sides by the 0.0283. 0.0323, where that 8 came from. Divide by 4, and then take the square root of both sides. We have an answer of 5.82 times 10 to the negative 6 is equal to x. Going back to our expression, in our ice table, the nitrogen concentration of the nitrogen monoxide gas was given to be 2x. So multiply that by 2. 1.16 times 10 to the negative 5 moles per liter. Now, when we compare this number here to 0.038, that's much, much smaller. If we take this number here away from that, we're gonna end up with 0.03799 something. So essentially, again, because the Kc value is small, indicating that the reactants are strongly favored, this approximation method does work for us. Okay, so I'm going to give you some time during the next period to work through this assignment, and I will be logged on. I am working from home today, but please log on during the chemistry unit, or the chemistry class today. As you can tell, something's not right with